Hey guys, in this video we're going to talk about Chapter 10, Section 1, Taylor Polynomials. So the first question you might have is, what are Taylor polynomials? Well, loosely speaking, Taylor polynomials are polynomials, so degree 1 linear polynomials, degree 2 quadratic polynomials, degree 3 cubic polynomials, all the way up to degree n polynomials, and these polynomials are used to approximate a function around a certain x value. Now, why would we do this? Well, as we've seen before, some functions are easier to work with than others, especially with respect to taking derivatives, integrating, and those functions that are easy to work with are polynomials, right? Much easier than functions such as natural log of x, sine of x, cosine of x, tan inverse of x. So it's just a way of working with easier functions. So that's kind of the motivation behind this. And just as a little side note, the Taylor polynomial, the Taylor series, was generalized by a mathematician named Brooke Taylor, and he came up with these ideas when he was working with oscillations. Sine and cosine functions model oscillations quite well, and so he was looking for a way to simplify some processes with that. So that's a little bit about the motivation. So basically, Taylor polynomials are just used to approximate more complicated quote-unquote functions around a point. And next time we're going to talk about Taylor series, which represents a function exactly. And we're going to talk more about the theory behind it and also where these formulas come from. But in this lecture, I just want to show you guys the mechanics of all of it, how to use the formula to approximate functions with polynomials. So let's get into it. All right. So first question we have, how can we approximate the function y equals e to the x near x equals 0 using a first degree polynomial, aka a line? So the notation that I'm going to use is this notation. So p sub n of x, and this is just a degree n polynomial that we're looking for. Okay, so I want to look for a degree 1 polynomial, which just happens to be a line, right? And the idea here is that if we put a tangent line to this point and we zoom in really, really close, it's going to look pretty much like the curve itself. Okay, that's the idea here. So how can we get the equation of such a line? Well, remember that for a line, we have y equals mx plus b. And b, it's pretty clear what b is. B is the y-intercept, and we can see that this thing is going to intersect the y-axis. That line is going to intersect the y-axis at 1. So b is equal to 1. And m, well, remember last semester when we talked about slopes of tangent lines? Remember that? That was the derivative of the function at a point. So in our case, m is just going to be the derivative of e to the x at x equals 0. All right. So the nice thing about e to the x is the derivative of it is itself. And so our slope is just going to be e to the 0, right? We took the derivative and plugged in our point, which is simply 1. All right, so m is 1, b is 1. And so our line right here, this little guy, this tangent line, is going to have an equation y equals 1x plus b. So this would be a linear approximation. So the way that I would write this with our new notation is I would write it like this. I would say since this is a degree 1 polynomial, I would say P1 of x is equal to, did I put b right there? I meant to put 1. P1 of x is equal to x plus 1. So that is our degree 1 polynomial. So this thing is going to approximate e to the x at points around 0. So let's see what that means here. All right, so how about we consider a point around 0? And I'm saying around, but what does that really mean? That's a good thing to think about. What if I plug in 0.01 in for x into this function that we found, this approximate polynomial? Well, if I evaluate that thing at 0.01, I'm going to get the output being 1.01. And the question is, how close is this to the actual value? How close is this to the actual value? Well, the actual value is just going to be e to the x, which is 0.01. And this turns out to be, this turns out to be 1.01005. So this is the approximate value with the polynomial we just found. This is the actual value. So they're pretty close to each other, relatively speaking. Now, what's really cool, you guys, is that the higher the degree polynomial we use to approximate, the better the approximation is going to be. And I'm not going to get into the nitty-gritty of why that is, but you guys should think about it, and next lecture I'm going to talk more about that. But yeah, so that was our first linear approximation of a function e to the x. All right, so let's do another example. It says find a first degree polynomial that approximates g of x equals cosine of x for x near 0. Okay, so I'm going to do the same process here. We're looking for a degree 1 polynomial, so p1 of x. And we know that degree 1 polynomials are simply lines in the form of y equals mx plus b. Well, when x is equal to 0, it's pretty clear that this tangent line that we're considering is going to have a y-intercept of 1. So b is equal to 1. And what is the slope of this tangent line? Well, the slope is definitely 0. We can see it on the picture. We can also consider the derivative at the point 0. So if I take the derivative of cosine of x, well, the derivative of cosine of x is just simply negative sine of x. When we plug in 0 to negative sine of x, we get 0 as an output. So our slope is 0 and our b is 0. And therefore, the equation of this line is simply y equals 1. Okay? So that's my degree 1 polynomial. Let's write it out here. So p1 of x is simply 1. And so let's consider different values of x around 0. Well, we know that our output is always going to be 1 here. So let's compare that to what we get when we plug in different values of x into g of x. So g of x is the function we're trying to approximate here with 1. And if I plug in something close to 0, how about 0.05? I just get the cosine of 0.05, and that's going to give me 0.998, which is pretty close to 1, right? That's fairly close. So this is our approximate value here. What if I plug in something a little bit further away from 1? How about, a little bit further away from 0 than the previous one. How about negative 0.1? I don't know why I wrote that a little bendy. Let's see. So here I get cosine of 0, negative 0.1, and that is going to give me about 0.995, which again is kind of close to 1, but it's not as close as this guy, is it? And what's happening is the further away we go from 0, the worse the approximation is. That's what's happening here. So what if I do g of 0.4? That's even further away than the other two above. That's going to give us cosine of 0.4, which is 0.921. So we can see the progressive, the approximation getting progressively worse. And so maybe let's make a note of this down here. The further we stray from x equals 0, the worse the approximation is. Okay. All right, so now what I'd like to do is I'd like to approximate this function g of x equals cosine of x with a quadratic. Because as I mentioned but didn't prove, as you go up in degree, your approximation gets better and better and better, and you can approximate better for further out values of x. So, just like before, I'm going to use the notation Pn of x, but since we're looking for a quadratic, we're going to call this P sub 2 of x. So we want a few different things for this to be a good approximation. Okay, first of all, we want the actual function and the approximation to have the same value at x, okay? We also want them to have the same derivative or the same slope at x equals 0. And finally, we want the same sort of concavity around 0, right? And so we want the same second derivative as well. Okay, so we want all three of these things, and this is how we're going to figure this out. So first of all, this is saying the first thing we want. The when we plug in 0 for the quadratic, we want that to have the same output as when we plug in 0 into cosine of x. Same idea for the first derivative. So P2 prime of 0 should equal G prime of 0. And finally, we want the value of the second derivative at 0 to be the same in the case of the quadratic and cosine of x. Okay, so now that we know what we want, we can do some computations here. Okay, so here is our curve, cosine of x in green, and this is going to be the form of the quadratic that we're trying to find. Now, this just looks like your basic quadratic. I'm just, what you'll usually see in like an algebra class is coefficients of a, b, and c. But here, instead of using a, b, and c, I'm using the coefficients c naught or c0, c1, and c2. Okay, so these guys are my coefficients of this quadratic. All right, so here is my basic quadratic right here, P2 of x. And if I take the derivative of that guy using the power rule, since this is just a constant that disappears in the derivative, a constant or a coefficient times x when I take the derivative is simply that coefficient, right? If we have 2x and I take the derivative, it's just 2, right? So that's the idea there. And then this last thing, when I take the derivative, it's just going to be 2 times c2 of x, just reducing x by 1 using the power rule. Then I can take the second derivative and get this guy. Okay, now considering the actual function, not the approximation, we have g of x equals cosine of x. Take the derivative of that and we get negative sine of x. Take the second derivative of that and we get negative cosine of x. So now we have everything we need to satisfy these three conditions right here. And that's what we're going to do right now. Okay, so the first condition we want to meet is we want to be able to get the same output for both the quadratic and the regular function at 0. So when I plug in 0 into my function up here, for x, I get the following. I get c0 plus c1 times 0 plus c2 times 0 squared, and that's going to equal g of 0. Well, g of 0 is simply cosine of 0. Okay, so now I'm going to simplify this stuff out. These guys go away, and I'm simply left with c0 is equal to 1. Let me double check my work on this because, yeah, that tracks. Okay, good. All right, cool. So we found the first coefficient in our quadratic. That's what we're trying to do. We're trying to figure out what these coefficients are so that we can model it. Okay. So the second condition that we want to be true is that the derivatives are equal at the point 0. Okay. So p2 prime of 0. Well, let's take a look at this derivative up here in purple. This is just going to be, so the left side of this equation is going to be c1 plus 2 times c2 times 0, right? That's our x. And that's going to equal g prime of 0, which is just negative sine of 0, right? Just looking at this side. Okay, awesome. So that goes away. And negative sine of 0, of course, is 0. And so we get c1 is equal to 0. Cool. All right. We have our first two coefficients figured out. Now we just need the third one, and bam, we have our quadratic approximation. Pretty cool. So now the third condition is we want the second derivatives to be equal to each other at x equals 0. So going back up here, we have that our second derivative is 2c2. All right, so we want 2c2 to equal, well, negative cosine of 0. Well, cosine of 0 is just 1, so we get 2c2 is equal to 1. Negative 1, sorry. And so c2 is simply going to equal negative 1/2. Awesome. So we found all three of our coefficients, and now we have that p2 of x, our quadratic approximation, is just going to be 1 plus 0x minus 1/2 x squared. So again, this is c0, c1, and c2. And this goes away because of that 0 multiplication by 0. And so our second degree polynomial that's going to approximate cosine of x is 1 minus 1/2 x squared, which is much easier to work with than a trig function in most cases. So that is it. So let's take a look at this on Desmos, our best friend Desmos. So in green, I have our function that we're trying to approximate, cosine of x. In black, I have the linear function that we found a few slides ago, which was just y equals 1. So it's that straight line. And then in purple, I have the quadratic function that we just found, okay? And you can see that for values of x further away from 0, the quadratic is a much better approximation. And so I'm going to write this down because it's so important. So the big idea here, and you guys should think about why this is true. The larger the degree of the polynomial, the better the approximation is. Okay, so that's the big idea here. All right, so this is a crazy looking formula. I realize that. And what I'm going to show you in this lecture is how to use it. I'm not going to go into depth of how it was derived. We're going to talk about that next time when we talk about Taylor series. But for now, I just want you guys to have this formula in your back pocket so that you understand the mechanics of it. Okay, so here's what it says. It says that we can approximate a function such as cosine of x, such as e to the x, with a polynomial function of degree n, and this is the way we do it. And this is, by the way, this is for x near 0. We're going to talk about a more general case in a few slides, but this is how we do it. We take f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial x squared, and so forth. The pattern just continues right there. We're going to do some examples with this just so you guys can see how it works. And we call this polynomial the Taylor polynomial of degree n centered at 0. All right, so let's take a look at how we can do this. And we already technically used this for this guy and for this guy right here, but we didn't use it with the actual formula. But let's do some examples where we do. Okay, so it says construct the Taylor polynomial of degree 7, approximating the function f of x equals sine of x for x near 0. And then we're going to compare the Taylor approximation with the actual value. Okay, so let's go ahead and look at that formula. Well, the first thing we need is we need all of these higher order derivatives up to 7. Okay, so what I'm going to do on this left side is I'm just going to start with f of x. That's just my basic function that we have, which is sine of x. Okay, now this is going to be boring, so skip ahead if this is boring for you. F prime of x is cosine of x. F double prime of x. We're going all the way to 7 here, guys, because that's what we're looking for, a degree 7. F double prime is negative sine. This guy just means I'm tired of writing I'm tired of writing those prime symbols, and so this is just notation for the third derivative. The fourth derivative is going to have a 4 and so forth. So, okay. So here we go. Okay, so those are all my derivatives up to the 7th derivative. Now what I'm going to do, because my formula, we need to figure out what f prime of 0 is, what f of 0 is, f double prime of 0, all that stuff. We need all of that. So again, you should verify this, but it's just basic Calc 1 stuff. We're just evaluating each of these, the function first and the derivatives at 0. So f prime of 0 is cosine of 0, which is 1. F double prime of 0 is negative sine of 0, which is 0, and so forth and so forth. All right, cool. So now we have everything we need, and we just need to utilize the formula. So the formula says, hey, we're going to start at f of 0, right? So maybe I'll write this out here. So maybe I'll write it down here, actually. So we have f of 0, and this is going to be P7 of x, a degree 7 polynomial. It's going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f3 0 over 3 factorial x cubed and so forth, plus fourth derivative of 0, x to the 4 over 4 factorial plus, here we go, okay. Okay, and finally we stop at 7. So f7 of 0, x to the 7 over 7 factorial. All right, now let's go ahead and plug in what we found in our column to the right. So f of 0 is just 0, that goes away. I'm gonna first just like clear out the 0 stuff. So like f double prime is 0, so this whole thing goes to 0. You guys see that? F to the 4 of 0 clears. That's all 0. F to the 6, f of 6 of 0 is 0, so that clears. And I'm just left with f prime of 0 of x. Okay, so let me rewrite this. So we have p7 of x. F prime of 0 we just found was 1. So we have 1 times x is x. Plus, now we're looking here, f3 of 0 is negative 1. Negative 1 over 3 factorial, x to the 3. Okay, now we have this guy. f5 of 0 is 1, plus x to the 5 over 5 factorial. Okay, that's gone. And then the last one is f7 of 0, which is negative 1. We found that here. Negative x to the 7 over 7 factorial. And actually, I don't need this plus right here. So this is my 7th degree polynomial that is going to approximate my function. And my function in question was sine of x. Let's see how good this approximation is when x is equal to pi over 3. So pi over 3 is kind of close to 0, but I don't know. I mean, it's 1 point something. It's not as close as as a lot of numbers, but let's see how good this approximation is. All right. So, here's our polynomial. And let's see. So the question is, how good is this approximation? How good is it? And what does that mean, good? That's a good question for you guys to ponder. Okay, so here we go. So P7 of x, well, we're trying to figure out how good the approximation is for x equals pi over 3. So that's what we're going to plug in for x into our polynomial that we just found. So we have pi over 3 minus pi over 3 cubed over 3 factorial plus pi over 3 to the 5th over 5 factorial minus pi over 3 to the 7th over 7 factorial. Now you can put this in Desmos to get a nice value. That's what I did here. I'm not going to do it again. Just don't want to bore you guys to tears. But if you put this in Desmos, you should get this. 0.8660212 71656. So this is my approximate value. And let's look at my actual value. So the actual value, well, is just going to be sine, right? That was our function in question. Sine of x, which is pi over 3. And if you put this in Desmos, it's going to give you this. So this is the actual value, which is very, very close to the approximate value. All right. And the point is, we used a degree 7 polynomial, which is much better than the lower degrees that we were using for cosine. So we're getting a much better approximation, and pi over 3 is pretty far out from x equals 0. So cool stuff, you guys. Here's a little visual for you. So in green, we have y equals sine of x, just our standard sine curve. In red, we have the approximate polynomial that we found, and it looks like it's pretty much layered on top of each other from, it looks like from -3 approximately to about 3. And so it kind of makes sense that the value pi over 3 had a very good approximation, right? Because this picture, I mean, they're basically laying right on top of each other at x equals pi over 3. So that's the idea here. All right, let's do another example. So here is our old friend cosine of x. We found a degree 1 polynomial to approximate it. We found a degree 2 polynomial to approximate. Let's get crazy and find a degree 8 polynomial to approximate this thing. And let's see. I'm not going to bore you with all of these derivatives. I'm just going to lay the table out for you and let you verify this, because this is just Calc 1 stuff. So, and hopefully this week will be a nice little break from all of those those series tests that we've been talking about, which I think they're super fun, but I know that they can be kind of challenging when you first see them. So this is a nice little throwback to Calc 1. So here we go. I'm just finding the derivatives all the way up to 8, the 8th derivative of the function I'm interested in, which is cosine of x. Okay. Just taking derivatives, doing what we do. All right, so there's the 8 derivatives along with the function itself. Now what we really care about is the second column. Again, we're looking at what happens near 0, so we're concerned with g of 0, which is 1, g prime of 0 is 0. Just plugging in 0 into all these derivatives to see what I get out. All right, that was a lot of work. Okay, so now I'm going to use my definition to figure out what the 8th degree polynomial is. Well, let's see. So I have the following. I have that my 8th degree polynomial is going to be g of 0 plus g prime of 0 times x plus g double prime of 0 x squared over 2 factorial, and so forth. Now what's nice is some of these are going to go to 0, so we don't have to deal with all of this mess. So let's see. Alright, so now I'm looking at this column to see where my zeros are. So g prime of 0 is 0, so the first thing I'm going to do is cross that out. g3 of 0 is 0, that goes away. g5 of 0 goes away. And g7 of 0 goes away. Okay, excellent. So now I'm just going to plug in the rest of my stuff. So I'm going to do it at the top up here. So my first term is g of 0, which we see as 1. So 1 plus double prime is negative 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x to the 6th, and finally plus 1 over 8 factorial x to the 8th. Okay, so this is my degree 8 polynomial that approximates g of x equals cosine of x. Got 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8th over 8 factorial. So that's our degree 8. Now, let's take a look at, what we found before. So in green, we have our function that we're trying to approximate. In blue, we have the quadratic function that we found a few slides back that approximates cosine of x. And in purple, we have our new approximation, that degree 8 polynomial. And we can see that the purple is going out much farther and lying flush with that cosine curve rather than the quadratic. Okay, so we can see that the purple curve is a much better approximation. It lies on the green curve much better than the quadratic. All right. Let's do another example here. Okay, construct the Taylor polynomial of degree 10. Now you might think, oh my God, Sarah, you're really going to do this degree 10? Yeah, I am, because e to the x is so nice. The derivative is always e to the x, so it's not going to be as crazy as we think it's going to be. Okay, so we want to check the accuracy at x equals 1. Okay, so we're trying to approximate e to the x with a Taylor polynomial. So we need our column here. We have f of x equals e to the x, f prime of x equals e to the x, and so forth, all the way down to the 10th derivative is going to be e to the x. That was easy. All right, now our other column, we have f of 0 equals 1, f prime of 0 equals 1. We're just plugging in 0 into e to the x, all the way to f10 of 0 equals 1. Super easy, right? Okay. So now our degree 10 polynomial, p10 of x, is just going to equal 1 plus x squared over 2 factorial plus x cubed over 3 factorial, ... all the way to x to the 10 over 10 factorial. So that's our polynomial. Here it is. And the question is, how good is this going to approximate x equals 10? Well, the actual value, when we do, x equals 1, you guys. The actual value, so this is the actual e to the x, so we're plugging in 1 for x. Well, that's just this irrational number, 2.718281828, okay, and there it goes. So that's our actual value of e forever and ever. And it turns out, I'm not going to show you guys this calculation, but the approximate, and you guys can check it on Desmos if you don't believe it, but the approximate value, p10 of 1, so when I plug 1 in for each of these x's, what I end up getting is 2.718281801. So it's very, very close to the actual value. Okay, cool. Okay, let's do another example. Construct the Taylor polynomial of degree n. So they just tell us degree n. We have n terms here. F of x equals 1 minus x for x near 0. So let's build our columns here. We have f of x is equal to 1 over 1 minus x. F prime of x. Well, this guy is the same thing as 1 minus x to the negative 1. So using the power and the chain rule, f prime of x is going to be negative 1 minus x to the negative 2 times the derivative of the inside, which is negative 1. And so these double negatives make a positive, so that's what I'm just going to get rid of them. All right, awesome. So f double prime of x, take the derivative of the above. Again, using the power and the chain rule, we get negative 2, 1 minus x to the negative 3 times the derivative of the inside, which is negative 1. So again, these negatives disappear here. Okay, how about f3 of x? So we're doing this until we can recognize a pattern here. Right, so f3, f for the third derivative here, again, chain and power, negative 6, 1 minus x to the negative 4 times negative 1, so those negatives disappear. Okay, so what's the pattern here? Well, let's go ahead and this is we're figuring out the nth polynomial here, right? So if I do, again, we're looking for around 0. So if I do f of 0, I'm just left with, when I plug in 0 here, 1 minus 0 is 1 to the negative 1 is 1. F prime of 0 is again just 1. F double prime of 0 is going to be 2. F triple prime of 0 is going to be 6. And keep in mind here that 2 is the same thing as 2 factorial. 6 is the same thing as 3 factorial. And f4 of 0 is going to be 24, which is the same thing as 4 factorial. So hopefully you guys are seeing a little pattern here. So again, you know, my p sub n of x is going to be f of 0, which is 1, plus 1 times x, which is just x, plus, well, this time we have 2 factorial over 2 factorial x squared. Then we have plus 3 factorial over 3 factorial x cubed. And then we have plus 4 factorial over 4 factorial x to the 4. All right, I think you guys are seeing where this is going. Plus dot 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 plus n factorial over n factorial x to the n. All right, so all of these factorials are going to cancel out. And so this polynomial that is going to approximate this function should look very familiar to you guys, right? So 1 plus x squared plus x to the third plus x to the 4 plus dot 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 plus x to the n. So this is simply a geometric series with a common ratio of x, right? And what we're going to see next time when we actually talk about Taylor series is that we have an infinite series representation of this guy right here, and the domain is going to depend on where the geometric series converges. So, pretty cool idea. But yeah, that's it. That's our polynomial of degree n that approximates 1 over 1 minus x. Okay, so this is basically the same formula as we had before, but we've been talking up to now about x values near 0. Now we're just going to talk about x values near a. So not necessarily 0, but could be another number such as 1, 2, 3, whatever. Notice that this formula is the exact same formula as before, except instead of a, we had 0, right? So 0, 0, etc. But this time, we're just going to use this in the general case. So we call x equals a the center of the Taylor polynomial. Okay, so let's do an example where the center is not 0. So in this example, it says construct the Taylor polynomial of degree 4, approximating the function f of x equals ln of x for x near 1. So in this case, a is equal to 1. All right, so let's do the same thing that we've been doing. So the function that we're approximating is f of x equals ln of x. The first derivative of this guy is just going to be 1 over x. The second derivative is negative x to the negative 2. Third derivative, using the power rule, is 2x to the negative 3. And finally, the fourth derivative is negative 6x to the negative 4. So this time, instead of plugging 0 in for x, we're plugging in 1 because that's our a. So f of 1 is going to be ln of 1, which is 0. F prime of 1, 1 over 1 is 1. F double prime of 1 is negative 1. F triple prime of 1 is 2. And the fourth derivative, plugging in 1, is going to give us negative 6. All right. So we have the following. We have P4 of x. It's going to equal f of 1, which is 0, plus f prime of 1 times x minus 1, which is just x minus 1, plus f double prime of 1, which is negative 1, over 2 factorial times x minus 1 squared, plus f, the third derivative is 2, so we have 2 over 3 factorial x minus 1 to the third power. And finally, we have negative 6 over 4 factorial times x minus 1 to the fourth power. All right, so we can simplify this a little bit. So let's do that. So we have x minus 1, and then here, this just becomes minus x minus 1 squared over 2, because 2 factorial is simply 2. 2 over 3 factorial, well, 3 factorial is 3 times 2 times 1, so that's just going to be over 3. So we have plus x minus 1 to the third over 3. And negative 6 divided by 4 factorial, well, 6... So we have 6 over 4 times 3 times 2 times 1. And so we have a 6 cancels out on top and bottom to just leave us with 4 on the bottom. So we have negative x minus 1 to the fourth over 4. And so this guy is going to be our degree 4 polynomial that approximates the function ln of x. So what if you wanted to approximate ln of 1.1 with our polynomial? Well, so we would just plug in 1.1 in for x, and then we would compare that value. So we'd plug in 1.1, and I haven't computed this yet, but this would be a good exercise for you guys to do. So put in 1.1 into this guy, see what that is, and then compare. So we have P4 of 1.1 equals something, and then compare that to the actual value. All right. Okay, guys, so that is the end of this short lecture. So that is how you can use Taylor polynomials to approximate some more complicated functions. Next week, we're going to talk about Taylor series. So we're going to talk about getting an exact infinite series to represent our function, and we're going to talk about the domain in which that, the series is going to be a valid representation of that function. Okay, guys, thanks for watching. I hope you guys learned something and enjoyed this video, and I'll see you guys next time.